All right, let's talk a little bit about Gibbs free energy, this term delta G, right? And so we use this term to sort of characterize chemical reactions as either spontaneous or non-spontaneous, right? We have two different graphs here, one showing spontaneous and one showing non-spontaneous. Now, before we get into that, the Gibbs free energy change, the delta, right here, change in Gibbs free energy, is really comparing the reactants to the products of these two sets of reactions. Okay? Now, Gibbs free energy, the change in Gibbs free energy, is actually a combination of two things. It's a combination of the change in bond energy, or it's also known as enthalpy, H, and the bond energy can actually go up. We can have more bond energy in the products than reactants, or less bond energy in the products than the reactants. Could be either direction. Um, in addition, we have this potential for an entropy change, this delta S term, which is multiplied by temperature, right? And so really the free energy change in a chemical reaction is determined by this balancing act between bond energy changes, delta H, and whether or not the system became more or less organized, if you will, right? That's the entropy change. Okay, well, again, there's a lot of complexity there, but we can think of this delta G as available energy to do work from a chemical reaction. And so if we look at a chemical reaction on the left here with a negative delta G, in other words, the products have a lower a lower Gibbs free energy than the reactants. In other words, the delta, the change in Gibbs free energy is negative. In that case, right, the reaction is termed spontaneous because we're going to give off energy in the process of converting reactants to products. Now we can ignore this hump for the meantime on both sides, and that's actually called the activation energy, right? And we'll get into that in a minute. That's what enzymes are really good at reducing for us and making these reactions move forward. But this reaction will be spontaneous on the left here. Reactants will be converted to products over time, and energy will be released. Now, in many cases, in biological systems, we want to harness some of that energy to do work or to drive another chemical reaction. The enzymatic pathways of glycolysis, a couple of the enzymatic steps in glycolysis, release enough free energy that we can add a phosphate group to ADP to create ATP. So we sort of swap bond energies there to create ATP, right? And so if we have enough energy released from an exergonic spontaneous reaction here on the left, we could actually use that energy to drive an endergonic or non-spontaneous reaction where our products are actually going to have more free energy than the reactants, right? So we have to have energy input for that to occur.